Welcome to the presentation of our paper Filter-Based Online System Parameter Estimation for Multicopter UAVs. My name is Christoph Böhm and I'm a PhD student in the research group Control of Network System at the Universität Klagenfurt. We have an increasing demand for plug-and-play ready UAVs with unknown configurations. And a significant factor to their success is the adaptation through self-awareness of the UAV that relies on accurate system modeling and identification. Hence, we present a Bayesian filter approach to online and continuously identify system parameters, sensor self-calibration states, and vehicle navigation states in a holistic framework. Our approach estimates a state vector of size 40 plus 7 times n rotors. It includes vehicle control states, sensor self-calibration states, inertial parameters, and geometric and aerodynamic parameters of each rotor. Newton-Euler equations model the system dynamics with the rotor speeds as input. All other states are static except the drifting IMU bias. Previous work often uses the artificial body frame as a reference, forcing assumptions on states such as principal axis orientation. Our system model eliminates those by defining the center of mass m aligned with the UAV's principal axis as its reference frame. Therefore, unobservable dimensions do not appear with this formulation. This work also introduces new states to the estimation with a full 5D rotor placement, including 3D translation and 2D spherical spin axis for each rotor. A general rank and null space analysis of the observability matrix O reveals the system model's observability properties. We analyze different combinations of pose, position, and IMU measurements with 1, 4, 6, and 8 rotors. It shows that IMU measurements already make a subset of states observable that allow for simple angular rate control. Using a pose or position sensor makes most of the state vector observable, except for the sensor self-calibration states not used. Interestingly, a position sensor is sufficient to estimate the center of mass attitude. Two recurring joint observable subspaces are present. The first one, J2, spans one dimension across thrust coefficients and mass, caused by the ratio of those states. The second one, J3, spans 1 plus n unobservable dimensions and is caused by the rotor's geometrical ambiguity and its influence on the rotational dynamics. Therefore, knowing one state in J2 and adding 1 plus n rotor-to-rotor distance measurements of J3 makes the whole system fully observable. Real applications might show different results because of state values and reference frame alignments. As stated before, using the artificial body frame results in unobservable dimensions in the translational calibration states. This is the result of different configurations having the same result in the estimation. The green springs connecting the body frame with the others visualizes this fact. Our approach does not show such unobservable dimensions. We support our claims through a series of simulation experiments where we perform 30 test runs with different Lissajous figure-based trajectories using a quadcopter. Gazebo rotors and a filter implementation in MATLAB are used for the evaluation. We chose to focus on the estimation results of the new geometric states seen in the left figure. The solid lines are the means, the shaded areas are the standard deviations, and the dotted lines ground truth. All estimates converge fast to an appropriate value, even with a wrong initial guess. Comparing the performance was not possible since, to our knowledge, no approach currently estimates these system parameters. All other states achieved approximately 24% better estimation accuracy compared to the state of the art. We repeated the test series with tilted rotors to great success. The empirical results validate the observability analysis and they can compete with state-of-the-art frameworks. To summarize, we presented a holistic Bayesian filter approach that allows online estimation of system parameters, sensor self-calibration states, and vehicle navigation states of a multicopter UAV with n arms. We do not use the artificial body frame, which benefits the overall estimation process. The observability analysis shows us that easily measurable a priori knowledge of the UAV setup, such as the mass and the rotor-to-rotor distances, makes the system fully observable with only a position sensor and IMU available. The sensor, inertial and aerodynamic states achieved approximately 24% better accuracy compared to the state of the art. Thanks for your attention, and if you have any questions, feel free to contact us.